Hello, can you hear me? Okay. I see. Yes. Okay, cool. Well, thank you very much for having me here. Oh, it's nice to be here in Florence. So thank you to the organizers for giving me this opportunity to talk to you today. My name is Ben Kitching-Morley. I am a final year PhD student at the University of Southampton. And today I'm going to be talking, that's better. Today I'm going to be talking about non-perturbative IR finiteness in super-renormalizable scalar quantum field theory. And specifically about this paper, which has the same name as the talk, by the LACCOS collaboration, of which I'm a member. This collaboration of researchers is defined by the list of authors here, plus Valentin Nouri and Lizzie Dobson. You'll notice that the majority of the researchers here are affiliated with either the University of Southampton or the University of Edinburgh. The purpose of the collaboration is to look at holographic cosmology models on the lattice, and I'll get into what those are now, I guess. So here's the outline of the talk. I'm going to start by talking about what is holographic cosmology and why we'd want to study it. And then I'm going to go on to look at the lattice simulations that we've done on these holographic models. And finally, I'm going to go through the analysis that we've done on these models to conclude that they are in fact infrared finite, which is the purpose of this study. So let's get into it. Cosmic inflation is a theory of the early universe, which solves three main problems: the horizon problem, the flatness problem, and the formation of structure in the universe. And it is a kind of testable theory. The most common variant of it is part of the lambda CDM kind of standard model of cosmology. And this relates to the power spectrum of the cosmic microwave background radiation. However, there are problems with this theory. It requires fine-tuning, specific initial conditions, and perhaps most concerningly, it's an effective field theory, which means that it leaves the question of kind of the initial singularity of the universe, e.g. the Big Bang, unresolved. So enter holographic cosmology. This is a full quantum gravity description of the early universe, where this four-dimensional cosmology is mapped to a three-dimensional quantum field theory, which is the holographic dual theory. It's built upon a DS-CFT correspondence, and we can draw a map like this, where this cosmology here is our real universe, and the QFTs over here are the things that we're trying to simulate on the lattice. And there is this way to connect between the two. Okay, so those QFTs in the top right corner of that diagram, which I just showed you, have a form of this action shown here. We have scalar fields, which are SUN valued. We have fermionic fields, and we have gauge fields. Now, this is a three-dimensional model, so therefore the coupling constant G is dimensionful. If we were to promote G to a field with an appropriate conformal transformation, then this action would be a conformal field theory. However, because we don't do that, it's not quite a conformal field theory. Instead, we say it has a property called generalized conformal invariance, which is the necessary condition for these holographic models. So we're interested in the infrared behavior of this model, which is, as I said before, kind of imagining going back towards the Big Bang. This is because time in the bulk is mapped to inverse renormalization group flow in the dual theory, is in, e.g. in this QFT. So going forward in time is like going into the UV of the dual theory. Okay. to be a bit more specific about how we could link the two between the real universe and this dual theory, we have this holographic dictionary, which relates 2-point functions of the energy momentum tensor in the dual theory to the scalar and tensor components of fluctuations in the cosmic microwave background radiation. Like so. Okay. So the problem with this theory is that it, at first glance, looks like ill-defined because it's super-renormalizable. From a simple power counting perspective, it looks like it's going to be IR divergent. And in fact, if one does perturbation theory, one sees that while it is finite at a one-loop order, when you go to 2 loops, you get a IR log divergence. And when you go to higher loops, you get polynomial divergences. It might not be a disaster though, because there is a finiteness conjecture, which came out in 1981, separately with Jakifin Templeton and Abelquist and Pisarsky, which says that the dimensionful coupling constant G can take the role of an IR regulator and enter in the log term like a log G kind of thing, which totally resolves the issues. Effectively, these divergences we see in perturbation theory are an artifact of perturbation theory. Okay, so this perturbative holographic cosmology models have been tested against against CMB data. The data suggests that we don't need to include fermions in the model. That's the first thing. And secondly, when you do the fit with multipoles greater than 30, which is the perturbative regime of the model, then the fit to the data is as good as lambda CDM, the standard inflationary model. However, lambda CDM has kind of tensions with the data at this kind of lower multipole region, and would really like to be able to extend our holographic cosmology models to the lower multipoles, where the theory is non-perturbative. But in order to do this, we're going to need a lattice simulation. Okay, which brings me on to the second part, lattice simulations. Okay, so we're going to start off with a simpler theory. We already said we don't need fermions, but we're going to start out without any gauge fields in our investigations. We're just going to do a simple pure scalar SUN valued theory. We now have this mass term here, and that's included in our theory because the mass term receives contributions when you renormalize and perform the renormalization group flow. So we need to include it in order that when we do renormalize, we can tune our theory such that the kind of renormalized theory is massless. Okay. So we've got 2 main goals. One of them is to check whether the theory really is IR finite and to test those hypotheses from the 80s. And then the second one is to, if it is IR finite, to find what the kind of mass parameter we need in order to get a massless point on the phase transition. Okay. So this is the details of the simulations we've done. We looked at n equals 2 and n equals 4 with a range of G, L, and M squared values. The kind of n equals 2, so the SU2 scalar field theory maps to O3 theory, which has been studied before, but the n equals 4 theory has no equivalent ON model. Now, the code and data related to this analysis are both open source and available on Zenodo from these links. Okay. I guess this may be a bit obvious, but there is a phase transition in this model. We can see it from just imagining sending this M parameter to plus infinity or sending it to minus infinity. If we were to go to plus infinity, we would find a symmetric phase. And if we send it to minus infinity, we'd get a broken phase. So we know that somewhere in the middle, there's got to be a phase transition. Okay, and as I said before, the holographic map is only valid at this critical mass point where there is this transition. So what we need is a way to quantify the transition so that we can identify it. And what we chose to use is the binned accumulant, which has been defined here. Okay. In order to kind of continuously evaluate this, we use a technique called multi-histogram reweighting in order to interpolate between the different mass points and identify the phase transition more clearly. This is a numerical trick to do with reorganizing the path integral, but it is analytically kind of exact, although you need certain conditions to be true in order to do this like without issues. Okay, so we think that the binned accumulant will follow, well, the binned accumulant is known to follow a scaling law, which means that it's some function of this unitless combination of things. Well, we've got the mass away from the critical mass divided by the dimensionful coupling constant and multiplied by this kind of scaled GL to the 1 over nu, where nu is the order parameter often defined when we look at kind of scaling towards critical points. So by doing a Taylor expansion on that ansatz, we can get a general expression for what we expect the mass value of the critical transition to be. And that is given by this green formula here. Note that in this formula, we've got an expression of MC squared GL, so this term here. And depending on whether the theory is IR finite or IR divergent, this will either include a divergent or a finite piece. So we have two different competing kind of ansatz about what this critical mass is. We're either going to have a log 1 over L, which is an IR divergent ansatz, as in as the lattice size gets bigger, the critical mass diverges, or we have an IR finite ansatz where instead the coupling constant appears in the log. Okay, so now onto the data and the analysis. Here's a look at the data. This is our binned accumulant across a range of different lattice sizes. And the x-axis here has been rescaled according to that, the unitless combination that we had inside the binned accumulant formula earlier. And just by kind of first glance, you can kind of look at this and say, well, it looks like it's IR finite because it's not moving when the lattice size increases. You know, we're able to line them all up on top of each other. So it's looking pretty promising at this point. But we probably shouldn't judge everything by appearances. So we will do a proper analysis on this. In fact, we attempted to do, well, we did do two analyses on this. We did a kind of frequentist analysis where we fit like a best fit function to the data and found the chi-squared, looked for the p-values and accepted or rejected based on some significance level. The second idea that we did was a Bayesian analysis, which involves integrating this likelihood function across the parameter range, which kind of more directly answers the question of which model do the data prefer. However, the problem with the Bayesian method is that there's always ambiguities in terms of how one defines priors, for example. Okay, so looking at the frequentist results first, we can see here that the IR finite, okay, so because we're trying to define the IR, we're looking at the large GL regime, basically. And so what we did was we include all data up to the maximum of values of GL, but then only include down to some cutoff value, which we call GL min. And what we tried to decide, well, we looked at the data and got us to tell us, is how far can we go down in GL min and still fit all of the data. So the lower GL min is, the more data that we're including in our fit, and therefore the better the fit is performing. And you can see that when it comes to the IR finite ansatz, we're able to fit to a much lower value of GL min, where we've included significantly more data in the fit than if we do an IR divergent fit to the data. And nicely, the critical scaling parameter nu for n equals 2 agrees with an O3 study done in 2001 by Hasenbusch, which is another confirmation that we're probably doing things along the right lines. Ooh, okay, so now to look at the Bayesian evidence. The Bayesian evidence comes from this idea of trying to quantify how probable is a model given some data. And to do this, you integrate the model across its model parameters, multiplied by your priors, which is this P of alpha given M. Okay, so the alphas are the parameters here. And then you apply Bayes' theorem to switch around this M of alpha given data to data given M. And this probability of data given M is exactly the likelihood function, L. So you get this expression here. And then if you take the ratio of this expression between two competing models, you get what's known as a Bayes factor, which is effectively the ratio of probabilities of the two models given the data. So if K were 100, that means that model 1 is 100 times more likely given the data than model 2, given the priors that you've put into both models. Okay. Now, how do we interpret these Bayes factors? Well, there's various different scales for doing this. One of probably the most standard scale is the Jeffrey scale, which comes from a book from 1939, but is used to this day. And effectively, if your Bayes factor is more than 0, it means your model 1 is more likely than model 2. And as the size of this Bayes factor increases, the support for the model increases from barely worth mentioning all the way up to decisive. Okay, when the log 10 of Bayes factor is bigger than 2. Okay, and then just a quick word on priors. This is always like a difficult thing, but when we have Gaussian errors, we generally try to define a uniformly distributed prior, although there's other reasons why you might not do this. Sometimes physics can give bounds on what choice of priors we should use. And even when that is not the case, we should at least try and use the natural parameterization of the kind of parameters in the model, because what a uniform prior a uniform prior in kind of one parameterization will become a non-uniform prior if we changed our parameters, basically, if we did a parameter redefinition. So we want to try and be in the kind of parameterization that seems most natural to the problem. And then in general, we want the priors to be as large as possible to capture as much of the likelihood as function as we can possibly do. So for example, in this study, we've chosen the parameter range to cover 10 sigma of the likelihood function in all dimensions, which hopefully is large enough. Okay, so here's the kind of punchline plot of the whole thing, and I'll talk you through it. So on the x-axis, we've got this GL min. So as we go from right to left, we are including more and more data into the fit. Now, on the y-axis, we've got two different scales. One of them is the Bayes factor that we were talking about before, and this is related to the color coding. So this E here is actually equal to log 10 of that Bayes factor. So when E is bigger than 2, we have decisive evidence for model 1 over model 2. Okay, so that's this, and these relate to these black circles. Now, we've also got on this diagram the frequentist analysis. So the IR finite ansatz is shown with the orange squares, and the IR divergent ansatz is shown with the green triangles. And you can see that, as stated before, the IR finite ansatz is able to fit much more data before the p-value becomes unacceptable than the IR divergent one. And this behavior is exactly matched nicely by the Bayes factor, by the Bayesian methods. We can see that as the kind of IR divergent ansatz becomes rejected in p-value, we also see significant Bayesian evidence for model 1 for the IR finite ansatz being preferred, which is nice. So these two methods kind of complement each other and pretty much agree. So we conclude that the theory is in fact IR finite. And then this is my last slide. I'll just give you a quick update on where our collaboration is at. So we've now updated our code so we can run on the next generation supercomputers. There's a new GPU computer coming online in Edinburgh called Tersa. And so we've got our code running on the GPUs there. We've also added gauge fields, and we hope to reproduce this kind of study with the scalar plus gauge model. And we've done the renormalization of the 2-point function between the energy momentum tensor and trace phi squared, which was also came out in a paper last year. Ongoing, we're repeating the same study with n equals 3 and n equals 5, with the view to take the large n limit, which we would like to do for the holographic models. And then the final renormalization of the energy momentum function, 2-point function, is underway, and once complete will allow us to exactly test against cosmic microwave background data and see if the model works or not. So no, see if we get new evidence or not from that study. So thank you very much for listening, and let me know if you've got any questions.
Okay, thank you very much. Questions, comments? I have a curiosity. Which was the size of a lattice that you used in your simulation? I don't know. I do not.
That was.
Remember if you.
Yeah, we went from
okay,
lattices between 8 and 128 cubes. Yeah.
Are there other questions? If not, let us thank again the speaker.
Thank you.